But what we really care about is what is our portfolio vol, because we're diversifying because we expect that we're going to get lower volatility by doing that. So in our case, we're getting a portfolio vol of 14.7. Now, this is where we get to do some learning, and we're actually going to go into the computing portfolio volatility, and I think you're going to learn quite a bit from this exercise, not just from the formulas, but also how it was implemented here in Excel. So let's just skip right to it. We're going to go to this learning page, and here we start when you learn about uh, portfolio vol, you always start with the two stock portfolio because it's easiest. And the reason for that is, first of all, this is the general formula. So you're taking the weight of asset A squared times the vol of asset A squared, which is the same thing as the variance of asset A, vol squared. You're adding that to the weight of asset B squared times the volatility of asset B squared, plus this strange term here, which is 2 times the weight of A times the weight of B times the correlation of A to B times the vol of A times the vol of B. That's the formula for portfolio vol for a our two asset portfolio. Well, we're going to work in variance space, covariance space. So what we're going to do is, to transform that, to transform these, get out of this correlation numbers here, we just look at the identity. And all correlation actually is the correlation of A to B is just the covariance of A to B divided by the vol of A and the vol of B. It's essentially taking the covariance between the two variables and then normalizing by each of their volatilities. So we just, if we substitute this for correlation, the denominator here, vol A, vol B, will cancel out with the vol A, vol B numbers here. And you'll be, instead of having the correlation number here, you'll have a smaller expression here that's just the covariance of A to B. And otherwise, everything else is the same. Now, we start with the two stock portfolio because it's pretty compact. But what happens as we start adding terms is we care about every single pairwise correlation in the basket. So if you have two assets, there's one correlation pair. If you have three assets, there's 3, 4, there's 6. And if you have 10 assets, you have 45 correlation pairs. It's just, I kind of wrote it here, it's just n choose 2. So you can just see the pattern here. As you add n assets, as you add another asset, the number of pairs increases by n minus 1 from the prior number. So you're going to start getting a lot of terms. So if we scroll down again, we just want to stay in covariance space. You get this formula right here. So you get this portfolio variance equals the sum of the weight squared times the variance of each asset. That's this first term. This is just the variance of each asset. You sum them all up, times their weight squared. And then this double summation of the weight of each asset, the weight of I times the weight of J, times the covariance of I to J. So this term, we're going to learn exactly how we compute this term, because this thing looks nasty, and we want to see, like, well, actually, how do you do this in Excel or in code? So we're gonna get to that. I just want to make one note here. Up here, we saw this term here has this 2 when we're dealing with the two asset portfolio, and we don't see a 2 here with the double summation. And the reason for that is this expression is actually this term here is actually 2 terms. It's really weight A, weight B times the covariance AB plus weight A, weight B times the covariance of BA. But covariance AB and covariance of BA is the same, so we can just collapse this into 2 times that. We don't have to do that. We don't need the 2 here anymore because the double summation is effectively handling the 2. So that's why these formulas look a little bit different. Okay, let's go back here and let's actually see how we do this. So remember, this was our formula for multi-asset or more than two asset portfolio vol. So this term here, remember, is just the weight squared times the variance of each asset. Well, when we create a covariance matrix, when you take the covariance of BETO to BETO, or GLD to GLD, or HYG to HYG, it's actually just the variance of that asset when you do the covariance of its returns to itself. That's just the variance. So all of this diagonal is just, those are just the cross terms between the same asset. So the diagonal, the sum product, or the sum of all these terms, is this term right here. So this is just the sum of the, and what you have on the row and the column next to it are the weights. Those weights come right from here. These are the weights in our portfolio of each asset, and we're just taking those and we're squaring the weights and times each of their variances, which is this red diagonal. The rest of these values make up the numbers of the sum product. So of the double summation, and these are just reflections of one another, right? So it's all getting counted twice. So VNQ and USO has this covariance, and then that's the same as here, and then this term and this term are the same. This term and this term are the same. So the upper right is a reflection of the lower left. So the double summation is going to basically add up the entire matrix. Now let's actually do this. So we go over here. Remember, we have the weights on the top, weights on the left. And what we're going to do is we need to grab the covariances for all of these terms. So we're going to touch this button and a little magic's going to happen. Watching everything get zeroed out. The labels get zeroed out, and then all the new covariances populate and the labels get put back on. So if you changed what was in your portfolio, these would also change along with it. And for paying subs, I'll give you the spreadsheet, and you can just open up this macro here and you'll be able to see how all the code works. So what did this do? What did this code do? So it went over to the log returns page and it changed this pivot table to include just the names in our portfolio. And these are all the log returns, and we're using 3 months of daily log returns, so 63 days approximately. And it's just looking up every set of pairs. So when it did BETO to GLD, it said it took this series and computed the covariance and then populated it back in this cell here, BETO to GLD. So once we have the matrix set up, then we actually need to do the summations. So this is what we're doing here is we're taking this row and we're sum producting it by this row. And then we're doing the same thing, this row with the second row. And again, we're just taking this number times this number times this number, this number times this number, and then we're summing it all across. And that's going to give us, there's 10 assets here, so this is going to give us a 10 by 1 vector. Each one of these numbers is the sum product of this row with this row. So the weights times the row. Excel is pretty cool. It has this neat function called matrix multiplication, mmult. And if you don't want to do the sum product for each one, you just do mmult. And what it'll do is it'll say, I'm going to mmult this set against this entire matrix right here. And even though these are zeros, it doesn't matter because the sum product, you're just summing zeros. It's okay that these are 0. And we end up with this, again, 1 by 10 vector. And the way you use mmult, you highlight the entire set here, you write the formula, and then you hit Control-Shift-Enter because it is an array formula. It is taking all of these values and multiplying it against each one of the rows in the matrix individually, and then generating this 1 by 10. That's step 1. I call it the intermediate result. Then we take the intermediate result and we multiply it, and then we just sum product this intermediate result with the weights once again. And that gives us this. And this is the variance. So step 2 is we've just computed the variance of this portfolio based upon the 3-month covariances and realized vols. And then to go from variance to volatility, we just go here, we take the square root. Remember, these were daily based off daily values. So we have a daily volatility of this portfolio of 93 basis points. And then we annualize by the square root of 251. Because of Juneteenth, it's 251 and not 252 anymore, right? So the portfolio vol is now 14.7, the annual portfolio vol. And if we go back here, that's the number that we have right here. And we can see that we get a nice little diversification benefit. We are getting a 14.7 portfolio vol versus an 18.9% vol if there was no offset of correlations, if all the correlations were one to one another. Now, I'm going to segue right here into the idea of index volatility because it's kind of a cool learning opportunity. If you imagine that S&P index vol is 15%, and the average weighted stock vol, so if you took the weight of every name in the basket times its volatility and summed it all up, you would get let's say that it happened to be 25%. So the average volatility of a stock in the S&P is 25%. If every single name was perfectly correlated to one another, then the index vol and the average weighted stock vol would be the same. Because what implied correlation is just the ratio of the index variance to the average stock variance. That ratio, the closer that this number is to this number, the higher the implied correlation. And if the index vol was only 5, even though the average stock volatility was 25, that would mean that there was a lot of offsetting correlations within the basket, right? So if these were the actual numbers, we can just say, let's compute the ratio. Well, remember, we got to do this in variance space. So we take the ratio of 15, you know what, let's actually do it one by one, equals this squared, drag it down, and then equals, there we go. So the average correlation of each stock to every other stock in the index would be a correlation of 0.36. And that would be the implied correlation if your index vol were 15 and your average stock vol were 25. We did the same exact thing here. We said our average stock vol is 18.9, this is just the raw vols. And then the portfolio vol is 14.7. Therefore, you can see that formula up here, right? Same idea. And we get an average correlation of each name to each other name of 61.6, basically. And a 0.6 correlation is is the diversification amount that you're seeing here between each stock and each other stock. And then I computed a Sharpe ratio just by putting in made up expected return assumptions for every one of these asset classes. And then that rolls up into an average portfolio expected return of 5.6% divided by a portfolio vol of 14.7, and we get a Sharpe's ratio of 0.38. So this basically is how you compute portfolio vol, and I think this is pretty fun to look at because you can now see, like, how is my portfolio performing every day? I have an idea of what its portfolio vol looks like. Maybe before it was kind of hard to track what your portfolio was doing, but now if you assign some proxy assets that we have volatility data for, you can now estimate a theoretical P&L for your book. Typically your portfolio might be hard to know what the daily P&L actually is because there's some stuff that you don't really have a proxy for. But if you do have a proxy for it, you can kind of build that, and we can very easily look at what the P&L would be if the proxy behaved if this proxy asset behaved like your actual holding. So this allows you to compute theoretical P&L. So you can see your portfolio risk, and you can see a theoretical P&L that is kind of hard to come by if you didn't go through this little proxy method. And one last thing I'll mention